Okay, so before I begin with this projectile motion example, I just want to talk about that I was going to involve calculus, and the main reason behind that is because I don't think physics can be taught without calculus. Just like physics can definitely not be taught without math, you know. And I know I've said that before, so just bear with me. This tutorials or videos or whatnot, whatever you want to call it. It is meant for anyone taking physics. Anyone, I repeat, anyone. So just stick with me to the end, and you'll learn a lot. You'll learn a lot more than probably just going to class. But go to class as well. You know, that way you get all the theory and hear what the teacher tells you. You know, it's always good to go to class, in my opinion. So, anyways. Since it is Sunday today, I'm going to try and do a football problem, you know, Sunday, 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 you know, so with this problem, all we're looking for is basically what angle range can this kicker who is kicking the football at 70 feet per second at 100 feet away, which is like 33 yards, you know, and what angles can he kick it from basically in order to make it still. So in the end, we're gonna just use the kinematic formulas that we like just learned. So anyway, to begin, we're going to start with the x direction. So typically it's better to start with the x direction for projectile motions just because you don't have gravity involved. Gravity only accelerates an object in the y direction. So the acceleration in the x direction is absolutely zero. So, you know, gravity points down. You know, it doesn't point like this where it has some x, and it doesn't point purely in the x. So anyways, so we're going to start with gravity. So I'm going to use the number one of all the kinematic formulas. So that's just the most famous one, and you're going to use that the most, like absolute the most. So we can do that for x and also for y, to be honest. So, and it just in the reality, all those kinematic equations I gave, all those should be in vector form as well. So I don't like to include as too much because it's just going to be too complicated in the end. But anyways, so we have delta x equals v naught in the x direction times by your time plus a half acceleration x direction times by time squared. So in the end, this is 0, like I said. So that's just, we get rid of this whole part right here. So what now we have to do is solve for time. So because we know what the delta x is, it's positive 100, and we know v naught x really. Well, it's we somewhat know what it is. So we know what the muzzle velocity is, which is 70 feet per second. So so in the end, I'm not going to write down any of the numbers I just said, just variables so far. So it's just going to confuse us later then. So really, we need the x component of this velocity vector. So that guy. So then this is the y. So using trig, this is going to be the cosine. It's going to be the adjacent side. So it's going to be v naught cosine of theta. So so like I said in the first video with components, you can write it where it's just the hypotenuse times by cosine, and that just equals your adjacent. So that's just the fastest way. So, and I'm going to be probably doing that from now on. So, and that's going to be times by time. Solve for time now. So we get t equals delta x over v naught cosine theta. So now let's do the y direction. So typically you do the x direction and solve for time, and then plug it back into here. So that's not always the case, but you know that it's a general rule, I guess. Not rule, but like it's a general tendency that happens. So anyway, so we're going to do the same equation right here, but with y. So it's going to be v naught the y direction times by your time plus a half, and then it's going to be ay t squared. So actually, since we're working with British units, meaning we have feet, you know, it's kind of weird. Britain uses SI and we use British units in America. Is kind of really weird, but but that's just because we used to be a British colony and whatnot. So that's history. I don't want to talk about history too much. So since we're in these, what I want you to do every time is just write down g equals 32.2 feet per second squared. If you write down this, you most likely won't you most likely won't write down 9.81 as your gravity, because that happens way too often. A lot of people are like, oh no, I was supposed to be I'm in feet, not meters, you know. So just write this at the beginning, just before you even begin, when it's just in British units. So it always happens where instead of writing 32.2, you write 9.81, but it's not it's hardly ever that other way. So to be honest. So anyway, so now this guy, so really it's going to be a negative g for this. So negative g. So I always use the g as just a number and then put on the negative. So get in the habit of doing that. Don't be like, oh well, this is technically negative. Don't do that. Don't do that. You know. So anyways, so now we're gonna rewrite this now. So we have delta y now equals v naught y, which is going to be v naught sine now, because we're working with the opposite side, sine theta times by time minus a half 32.2 and then t squared. So of course we know what time is, but it was not implemented just yet. So anyways, delta y is then going to equal v naught sine of theta, and then we have delta x v naught cosine of theta. V naughts cancel. So, and then we have minus, and then I'm gonna just write 16.1, just because that's what 32.2 divided by 2 is. So, and then we have delta x. So I'm just gonna, yeah, I'll just do it this way. So v naught cosine theta squared. So now, in the end, this is just going to equal, so sine over cosine, if you remember in your trig identities, that's just tangent. So it's going to be delta x tangent theta, and then minus 16.1 delta x over, well, delta x squared over v naught squared, and then cosine squared in the denominator is just going to be secant squared in the numerator. So it's going to be just secant squared theta. So so anyway, so now let's just implement all our numbers. And another thing is we need to use a trig identity for secant squared. So so 1 plus tangent squared theta is going to equal secant squared theta. So this basically comes from the trig identity cosine squared plus sine squared equals 1. Just divide everything by cosine squared, and you'll get this guy in the end. So anyway, so we're going to substitute this in here, and then we'll just have tangent thetas in the end, so which is going to be super nice. So so what I want to also figure out is what the hang time is, and also the angles, so which it can be from. So anyway, so now we're going to implement all our numbers. So delta y is going to be 10, because we're going up 10, and we're going, and then delta x is going to be positive 100, because we're going in the positive x direction. So it's like this is where our coordinate system is. So, anyway, so that's going to be 10 equals, so 100 tangent theta minus, so really, let's get the calculator out for this part. Okay, 16.1 and then times by 100 squared, and then divided by 70 squared. So what do we get? 32.9 basically. So minus 32.9, and then it's going to be 1 plus tangent squared theta instead of secant. So so anyway, so now basically what we're going to do is use the quadratic formula from the last video I made. So so in the end, we got to get constants, and we got to get x's, and we got to get x squareds. So I'm not going to use x for this. I'm going to use L. So just because we use x everywhere here. So L is technically going to equal tangent theta. So so in the end, 0. So from this, 0 equals, so we have to subtract negative 10 to this side, and then we have 32.9 also over here times by here, and that's our constant in the end. So minus 10 to here, and we get negative 42.9. So that's our C value, plus 100. Now I'm just going to write L instead of tangent. So, and then it's going to be minus 32.9 L squared. So, so now we can use the quadratic formula on this. Yay! So, so clear, or no. I'm going to use second answer for that. It's yeah. So if we go to program, go to quad, enter, and then so A, bring this over here. A is just is this guy, so that's going to be negative of our answer. So second answer, and it's taking this value if anything. So well, I know that for sure. So I've done this plenty of times. So and this is going to be 100, and then it's going to be minus negative 10 minus second answer. So so in the end, then we get these two values. So anyways, L is then going to equal 0.5160 or 2.527. So now if we do second, or no, if we just do inverse tangent, yeah, I guess I need that. If we do second answer, it's going to just do the bottom one, by the way. So I'll just do that, or I'll just do them in order. So point, because I have them in order right here, so that we know which thetas goes to which. So 0.516, and then that's going to be in degrees, because I have my mode in degrees. So you get 27.29 degrees. So theta equals 27.29 degrees, and that corresponds to the 0.5. So and then we have here, let me find it. Okay. So we have also, so just do second entry. So it's going to be 2.5274, so we get 68.413 degrees. So it's just 68.4. So I guess I should be focusing a lot more on significant figures, but like when you do it in like like online, if you do your online homework and you click submit, usually it's like within 10% or something. So it's like doesn't even take an effect. Or but a lot of professors aren't too worried. It does bring it to a little bit more accuracy, but you know, I don't know. I'd rather be more sane and I don't know, get more problems correct, I guess, than have to worry about that. So that's in degrees. So or here, 1 degrees. So as you can see, if he has a lower angle, it's gonna barely get it. But if he has a higher angle, then he's gonna barely get it again. But it's just gonna have more hang time, you know. So this is the lower angle, and then the higher angle would be like this, and it come down and be like right there. So most kickers would not go for, well, I guess either of those. Everyone just wants to make it in the middle, at the exact middle. So anyway, so we also need to get the time associated with these guys. So really, we just got to plug these angles into here. So and then this is just 100, and then this is 70. So really, it's just 10 over 7. So it's gonna be 10 over 7. Or no, I'm just gonna do it on the calculator. So and you'll watch. Okay, so yeah, I'll just do second answer for that one. So make some room. So it's going to be 10 divided by parentheses 7 cosine second answer, and then yeah, so you get 3.88 seconds. And then second entry, and then instead of answer, we're just going to plug in 27.29. So 27.29. So then we get 1.607. So like I said, with the smaller angle, you're going to get less hang time, and with the larger angle, you're going to get more hang time. So, and another thing I want to note right before I end this is that if you want the ball to go the farthest, you could do some derivatives and whatnot with this, I guess. I don't know. See where the delta x is the max, but in the end, what you want to the best angle to shoot something from is a 45-degree angle. So that way it has plenty of hang time, and it gives it plenty of forward velocity, meaning that has a very large delta, Vx. So yeah. Okay, so sorry once again, I want to say one last thing. I feel like I'm going to say that for every video like 10 times, but I need to say one last thing. Is that yeah, I just am doing one projectile motion example right now, but later on, like with the free body diagram examples, I'll be doing a lot more projectile motion examples. So I just want to basically give you everything that you need to know before you start working on a bunch of problems. So you need to walk before you run. At least that's how I think about this. Okay, so I'm back once again, and I totally called it, but yeah, I have one more thing to say. One more thing to say before I end this video. And basically, since like I just said that I'm not going to be doing projectile motion for a little while, more of the examples are going to be at the end of this video series in general. But basically, I just need to teach you every little aspect, and then we'll put it all together at the very end. So anyways, like what I'm gonna do, since I'm not gonna be doing too many of these, is I'm just gonna go over each step that we've done, because a lot of this when it's explained gets lost in the transition, you know, the at least the big picture of it. So I'll just go over each of the steps once again, and I'll probably be doing this more often in other future videos. So anyways, So we start off with this one, and we just used the most common kinematic equation, but we used it for x to start off. No acceleration in the x direction, because it's projectile motion. And then, so we have this function, and we were able to solve for what time is. So anyways, now we did it with y, and then from there, we just implemented what time was into all of them. And then now we have delta x's, delta y's, and v naughts, which are all in the prompt, basically. We know the muzzle velocity, the height, and then the distance that we need to go. And then we also have the angle and this, basically a bunch of sines and cosines and whatnot. So anyways, we were able to basically plug in our numbers and then basically convert everything just to be tangent thetas. So we used the trig identity right here, and we got it like this. And then, so in the end, we replaced tangent theta with L, solved for what L is, and then solved basically for theta in the end. And then plugged in theta to get our time. So, and that's mainly it. So.